All right, people, welcome to Organic Chemistry for Chemistry Olympiad. We're about to get started in like 5 minutes. So for you fellow YouTube watchers, dude, did our video even get any views on YouTube? Let me check. Let me check if you fellow Chemistry Olympians are actually watching the replay because we give very important information on it. Oh yeah, 10 views. Look at that. 0.7.
What is it? It's LHS Chemistry Olympiad.
Lambert HS Chemistry Olympiad, and the video title is Chemistry
How many
Olympiad.
subscribers do you have?
0 subscribers, 0 likes, 0 dislikes, 0 comments, but we do have a
I'm
10
gonna
views.
subscribe.
All right.
You gotta subscribe.
Yo, Arjun, what's up?
Yo, I'm gonna turn on notifications.
Yo, what's up?
Just getting ready. You know how it'd be. Oh yeah, let me make a starting slide, like a sit tight or something. We'll get started soon, and I'm gonna start sharing my screen. All right. This will also be recorded and put on YouTube. I'm gonna try to not drone on like I did last time when talking about electrochemistry. I hate electrochemistry, honestly. Terry, how many meetings do you think we should have before the end of the year? After this? At least one. We could maybe fit two, but
Yeah, maybe two. I guess it's like mid-November. We could probably do one.
don't think that there's Thanksgiving break that we have to worry about.
I guess we can do one like before Thanksgiving break. Maybe.
Was the Thanksgiving break already like in 2 weeks, so we'd have to do it the week after. Yeah, I'm pretty sure Thanksgiving break is gonna be the 23rd to the 27th.
Okay.
We could just maybe do like very early December, like December 2nd, and then do in like on December 9th, like the week right after maybe, and just get two meetings back to back in terms of weeks. I don't know. We'll see. We'll have to plan.
Yeah, we will. We'll definitely plan that out.
Yeah, we'll definitely plan that. Hey, can one of you Lambert people tell us if Lambert opened up today or does it open up tomorrow?
Open today.
Today? How was it? Were people like scared of like being near each other?
Not really, just stayed the same.
Yeah. It's probably gonna have another lockdown soon if I'm gonna predict. I was talking to this kid from South Forsyth and he said they're probably gonna have to shut down soon as well because cases are going up there. We need that vaccine, yo. We need that Pfizer vaccine.
It's true. Pfizer's gonna save us.
Dang. The European Union is gonna buy 300 million doses
90%
already
is a game.
of the vaccine.
There's like 600 million people in Europe though, in the EU who live in the
Well,
EU. I
that's
think.
pretty good though, right? Um, like they're already agreeing to buy that much. It's about, I guess, dispersal of it. Welcome everybody. You guys might want to pull out like a piece of paper or something and a pencil for some of the questions because you have to like draw it out because we're talking about organic chemistry. Um, so maybe have that ready. Yo. All right, we'll get started in like a minute or so. I hope everybody's doing well and you stay safe as Lambert opens back up. Um, I don't know, get tested, wear a mask, social distance, don't cough on people. Uh, and we're being cautious here, and we're gonna keep having virtual meetings. Honestly, probably we'll continue into second semester having virtual meetings, because I don't think the situation is gonna get, unless the vaccine like starts coming out super quickly or something, everybody gets it. We should probably be taking the same precautions we took this semester.
Yeah, I think the Olympiad is already online. I think it posted out some information some time ago.
Oh, did they? I didn't even see that.
Let me check. Okay, so in light of the continued uncertainty caused by COVID-19, both the local section and national exams will be offered virtually. And there's no lab portion for national exam again.
Yo, that's good, right?
Yeah, uh, so basically, just don't practice for the lab. If
Yeah.
any of you are already practicing for it.
Yeah, so you guys just have to know about chemistry. You don't have to know how to do chemistry, which is good. All right, I think we're gonna get started here. So this meeting will be about organic chemistry. Organic chemistry is a really big topic. Obviously, there's entire classes devoted to it. Terry's taking a class in organic chemistry. I'm taking a class in organic chemistry. There's a lot more to what we're going to cover here. Unfortunately, you can't cover it all in a 1 hour meeting. But we're going to sort of just introduce topics that we sometimes see on exam questions. And you could also maybe get a sense of like how easy or how interesting you find organic chemistry. And then hopefully you'd like try to look into it yourself. The Zoomdal textbook has a chapter on organic chemistry. I think the very last chapter, and it's pretty good. It's a good introduction. It's probably going to cover some of the same stuff we talk about here. But if you really want to start learning about organic chemistry, there's others textbooks like Organic Chemistry as a Second Language, which is pretty good and also not too difficult to read. And then there's more complicated textbooks that go over it. So it's up to you how much you want to go into it. But keep in mind, organic chemistry section in the local exam is not that big of a section. I think you're better off using your time to really perfect your AP chemistry knowledge, and maybe some of the other stuff that's not really covered in AP chemistry, but isn't organic chemistry. We're going to talk about here might get you like a couple points on the local exam, and sometimes that can be the difference. So organic chemistry is really the subsection of chemistry that's just dedicated to study of carbon compounds. So pretty much anything that just like anytime you see like carbon chains or carbon rings and stuff like that, you're talking about organic chemistry. And carbon is um, super useful. A lot of different types of compounds here. There's 16 million um, that we, I guess, as a scientist community know. But it's important because the carbon-carbon single bond and the carbon-hydrogen single bond are very strong. And so that means that carbon compounds are going to be very stable. That means you can store them, you can do stuff with them. And as you probably know, organisms are made out of basically just all carbon, at least for a lot of important macromolecules. Um, and the fact that carbon can form like four bonds, for example, means they can make very complex structures, including things like rings. And you can also do double bonds and triple bonds, and there's a lot of flexibility to what you can do with carbon, which is why it is so important. So beginning with sort of a very basic explanation of the names given to carbons. A carbon chain is usually referred to as an alkane, and depending on how many carbons you sort of add onto this chain, and you can see here in this table, um, you're basically adding CH2 to each time. So we started here with CH4, and then we sort of make CH3, CH3, then CH3, CH2, CH. And you have to, what's really happening is that the carbons are sort of connected to each other, and then you have hydrogens that are coming off of each carbon. Um, and as you stretch out this chain, you're basically just adding one carbon and two hydrogen every time. And so this is sort of a table of carbon chains up to 10 carbons and the names that we give them. So methane all the way to a decane, and it sort of uses, um, at least starting with pentane, pentane, hexane, heptane. All those are probably easier to memorize um, because it's just the prefix there makes sense. And then you can see here the overall molecular formula, and here's the more spread out and split molecular formula. And so yeah, alkanes you want to be very comfortable with naming, uh, knowing what a methane is, what an ethane is, a propane and a butane too, and being able to spot those in other carbon compounds because sometimes they're sort of like split off from the main carbon chain. You might have like a methyl that's sticking out of a longer chain, and we're going to see some examples of that. Uh, and so an alkane is given to carbon-carbon single bonds, or like a carbon chain that's made of just single bonds. And you use this suffix ane. So we've already seen a methane or an ethane, things like that. Whenever you have a double bond within your carbon chain, so you can have a carbon chain with a bunch of single bonds, but if two of those carbons are bonded together with a double bond, the suffix that you start using there is ene. And so this is called an alkene. And examples of that would be like a methene, or actually, I guess there's no such thing as a methene, but there is an ethene, and like a butene and propene, things like that. And then the third one would be a triple bond. If you have a triple bond there, they're a little bit rare, but they do sometimes happen. You use yne, and so there'd just be something like ethyne, butine,
Yeah,
stuff like that.
butane, propine.
Yeah. Usually, I don't know. It's kind of rare to see triple bonds, but they are there every now and then. And before you really get into organic chemistry, you need to be 100% confident with looking at what's called like skeletal formulas and sort of these skeletal structures. So since we're dealing with so many carbons here, our structure will just straight up not write AC. And so you can see here, turning these compounds here into the skeletal formula, you omit the C's. And also, uh, every carbon that's sort of like by itself with nothing added to it, you'll just assume that it has enough hydrogens to fill its octet. So remember again, an octet means that most atoms, or most atoms that we care about, can have 8 electrons in its field, in its orbitals. And so that corresponds to like 4 bonds usually, um, in terms of carbon. And so we just assume that if we have like a carbon, for example, in these pictures here, we have carbon that's bonded to two other carbon. We just assume that then we also have two other hydrogens coming off of it. And so you can see over here the full picture on the shortened structural formula. You can see you have the two hydrogen there, but here we just omit it again so that we can sort of get to the more important parts. And so also in these pictures here, you can see these two lines. I mean that there's a double bond. And whenever you have an actual letter there that represents, instead of a carbon, you actually have that element. So here we have nitrogen and oxygen. Um, but yeah,
Yeah, so this is IUPAC naming guidelines. So IUPAC is like the general, like the standardized chemistry naming. I don't believe there's any other like really major naming guidelines. So this is the one that pretty much everyone recognizes. So Oh, I think there's like a transition that you might have to click, you know.
Oh, yeah.
Yeah. Basically, how you might be wondering like how you name these like really long carbon bonds, like how you name these molecules. So, you first have to find like the longest carbon chain, and then you like that corresponds with the table that you saw earlier. So like meth, eth, prop, but, pent, and hex, and that's all the prefixes you use. And I'm kind of gonna speed over this, and then I'm gonna give you like an example toward the end. It might be easier to understand. So I guess go to the next slide. So and then basically you just follow these steps, and then you can like name what a molecule is. So you so the first step was like getting the prefix and then also the suffix. So obviously there's like the alkane and there's the alkene and there's the alkyne. So alkane is the single bond, the alkene is the one that has the double bond, and then the alkyne is the one with the triple bond. Um, and then there's some other steps. I guess you can just go to the next slide. Um, yeah, so actually, okay, just go to the next slide. There's an example on the next slide. It might be easier to understand.
Hmm.
So, okay, so we're going to cover how exactly you name this compound that you see here. So, the first step to naming is you have to find the longest carbon chain. So you have to find the longest. It has to be continuous. So you have to find the longest continuous chain of carbons. So you start at 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you count 9 carbons. So I mean you can also if you want to count the longest chain, if you go like the opposite way. So if you start from the very bottom, 1, 2, 3, 4, 5, 6, 7, 8, you obviously still get 9, and then there's some branches here, and then obviously that would be if you try to go down the branch, it would be a lot shorter than the longest one, which is the one that you see here. So yeah, first step is always count the longest chain, and that's going to give you your prefix. So since you know there's 9 carbons in the longest chain, it's going to be a non-name. So I guess go to next slide. Okay, so from this non-name, now you have to go ahead and name what all these different things attached to this longest chain is. So you have the Cl, you have the CH3, you have the two CH3s here. So what the CH3 is called a methyl, and then chlorine is just called chloro. So
Yeah,
um,
yeah, and the
ba-
methyl name comes from methane. So if you remember, a methane was just a CH4, so it was one carbon. Um, that name methyl just comes from taking that and putting a YL at the end.
Yeah, this also goes for if you have even longer branches. So for example, if you had at position 3, if you had like if you had a longer one, it could have been ethyl group or propyl, like even longer. Basically, um as long as you want, you just add the YL at the end, and that gives you your group. Um, I guess go to the next slide. Um, so here, the thing is, you basically have to count from 1 to 9. How exactly you're going to name the positions for everything. So how you determine this is you want to find like um, the busier side, so like more groups attached side of the molecule. So in this one, you can see that like if you start from this direction, there's like way more stuff attached like early on. But if you start from the bottom direction, there's like a lot less stuff, and everything is attached at the end. So you want to start with the side that has like more things attached to it.
Mhm.
Um,
Yes, so here
yeah.
like you see like the first substituent or the first group that kind of comes off is at number 2. When you're going from this direction. If you were to go from the other direction, it would be like only at the fourth that you'd see. And so that's why you start with this side.
Okay, and then now finally, you just have to name the position for everything. So once you start here, you have what that's position 2, you can see there's like the chloro attached. So you put 2 chloro. And then since you have 2 methyl groups attached, you'll put dimethyl, and then you indicate the positions. So there's 1 methyl at 3, and there's 1 methyl at 6. So it's 2 chloro, 3, 6, dimethyl, and then you add at the end the longest carbon chain, which is the nonane. And because this is all single bonds, there's it would be just ane. If you have like a maybe a double bond between like one and two, it would be an ene. But in this case, everything is just single bond. So it's 2 chloro, 3 6 dimethyl nonane. Do any of you have any questions about like how we named it, or are you guys all good?
There's a lot of like sub rules that you sort of have to know if you really want to know how to name every single compound, but it's like super complicated and like most people don't even memorize it by themselves. Um, but like this is the overall way of thinking about it is longest carbon chain, um, then find which direction, which orientation you want to go in from 1 to 9 or 9 to 1 here, and then know how to name the groups that are coming off of it, and then just put it all together into that.
Oh, you also might be wondering, like, maybe you might have been wondering, what if I put like 3 6 dimethyl before the 2 chloro? So, if you're wondering if it's like 3 6 dimethyl 2 chloro nonane, well, that's actually not right because you have to follow alphabetical order. So, C comes before D. So you first write, you start with uh, the lower one in alphabetical order.
Mm. Okay.
So there's like a couple different functional groups. So what functional groups are? They're like the other things that can possibly be attached. In the previous one, you had the chlorine attached, so that was just chloro, and then you also have all these other different groups of like what can possibly be attached to the giant carbon molecule. So I removed a couple of these in the slide. I just whited out because like they're not really useful. But these are some of the ones that like I'd recommend you memorize for the chemistry Olympiad. So first of all, you have your alkene, so your double bond, and your alkyne, which is a triple bond. And then you have an alcohol here. Alcohol is basically at the end of your carbon chain, you have like a OH attached to the end. And then that gives you your suffix. So that would be an OL suffix. And then ether is if you have like an O in like the middle of your carbon chain. So okay, so the alkane here, if you look at the alkane, that was the chloro that we had the previous slide. So so an example would obviously be 2 chloro. So that's a haloalkane that applies for pretty much all your I guess
Halogens.
your halogens is what I meant. And then you also have these other groups here. These are just some of the things that you kind of have to memorize. And then after you have this memorized, it should be pretty easy to know like what group is what. So yeah, next slide.
I just wanted to say, like, yeah, these functional groups, this is not the first time you're going to see this. You're going to see this a lot more because functional groups are really important in terms of like chemical properties for a molecule. So like carboxylic acid, for example, has acid in the name. So if you have a carboxylic acid within your molecule, most likely you're talking about an acidic molecule overall. And you're definitely going to need to know that type of stuff later. And also the only thing I think we should mention is like these R's that you see here and all these things. That just means like the rest of a carbon chain. So instead of having to like write out like an actual carbon chain, you just use R to just signify, okay, there could be more stuff here. There could be like more carbons and a bigger carbon chain, but we're gonna just omit it and put an R.
Okay, so here's a quick review of naming how you put everything together. So you start with the prefix first. You have to look, and then the prefix comes from the number of carbon atoms in like your longest chain. So meth, eth, prop, bu, pent, hex, hept, oct, non, and dec. And then this will give you your prefix, and then you can have a prefix before that, as you saw in like the example that we named. So it could be one of the halogens, and then that's part of the prefix. And then now we get to the suffix, and how you name the suffix is based on like what kind of like functional groups are attached. You could have multiple suffixes put together at the end. And so, obviously, so if you have any of these functional groups, and also like whether it's an alkane, alkene, alkyne, will determine what you put at the end of your name. So, so for example, if you just had a really simple like CH4 molecule, so that's just like one carbon, that would just be methane. Could because it's because it only has it doesn't have a double or triple bond. It's like it's a single bonded thing. So yeah, that's basically it. So how would you draw one pentanol?
Yeah, and I'm gonna go back here and show the like the cheat sheet. And I'm gonna type in the chat what it said. And see if you can figure out if you want to draw on paper, what one pentanol would look like.
Oh, I'll give you a hint about this one. So basically, you could also technically write it as pent one ol. So it basically means that if you look at the suffix here, it just means there's an alcohol group at position one on your carbon chain.
Hmm. And an alcohol is just a like OH bond like this.
Yeah, I guess we can just go to the answer since like they can't really answer in chat. Yeah, so this is basically what one pentanol is. So you obviously count the longest carbon chain, and you obviously don't count the OH because like that's not a carbon. So you start from one, two, three, four, five. That's the longest one, and so that gives you the pent. That's the prefix. And then how you get the suffix is the functional group. You have the OH here, so it's an alcohol, so it's pentanol. And then now you have to specify what position the ol is. So it's pent one ol, but for simplification purposes, we just move the one up to the front. So it's one pentanol.
And also there's like no double bonds or triple bonds, so it's just you don't have to worry about that.
Um, okay, so this is one of the questions from the chemistry Olympiad, and then like this is a drawing of the molecule, and then can any of you guys name it? Oh, maybe we can go back and reference the.
The functional groups.
Yeah, yeah, we should probably.
And so here's the cheat sheet for functional groups. If this will probably help you. So I'm going to show again the structure, and like try to think of what like matters here, like what functional group is present here. Uh, and then I'll go back here to the group chart and see if you can spot the one that's in that molecule.
Okay, I guess I'll give you guys a hint here. So the group is oh okay, show them the choices I guess first before I give them a hint.
Yeah, so put in the chat if you have an idea of what the answer is.
Yeah. Yeah. It's pentanal. So yeah, it's. I guess you can go back to previous slides so we can
Should
reference the
mhm.
structure. Okay. So basically here we first like the longest carbon chain. So 1, 2, 3, 4, 5, and then so that gives you your pent, and then you have this like aldehyde group here, and then that gives you your al. So that's pentanal, and yeah, yeah, that's it. So you have
And
pentanal.
yeah, and a lot of times when you have just one like functional group, then it's always going to be like at position 1. So even sometimes they just omit the number, and that's I think what happens in this question.
Yeah, it's just a simplification here.
Yeah,
Like,
it's just assumed. Okay. Okay, so now we've talked sort of about how to name structures. I guess we'll talk about structures themselves. So you've probably heard the word isomer before. It's sort of you learn it at the very beginning of your chemistry class, and then you never really talk about it too much again. But the idea of what an isomer is that you have two molecules that have the same overall molecular formula. So they have the like same number of the same type of atoms, but actually they have different structures. Like maybe those atoms are bonded in different ways, and so they produce different structures overall. And so here you have an example of, so you have here 1, 2, 3, 4, 5, 6 carbons, and so this would be like a hexane, but um, you can see here that actually you can come up with different ways of putting 6 carbons together, and the name also changes. Like these structures here no longer become hexanes because the longest carbon chain, for example, is no longer 6 in these examples. But you can also see the same thing happening here when you put like other non-carbon and non-hydrogen atoms or elements. So here you have ethyl alcohol, which has an OH here at the end. But you can have the exact same number of carbons, hydrogens, and oxygens, but have it be in dimethyl ether, which looks like this. Um, and if you have good memory, you might remember like alcohol and ether here were functional groups from before. So the ether was this oxygen that's in the middle of two like carbons like this, and alcohol was the OH. So you can see sort of there the names happening. But the importance of this is that obviously these structures are different, and so their properties will be different as well. And they will have both different chemical properties and physical properties. And again, you might remember this from like honors chem. Your physical properties is going to be talking about stuff like melting and boiling points, and it usually has to do with like the distances between different atoms. Um, while chemical properties has to do with reactivity and how like different molecules can bond with each other. Uh, but if you have constitutional isomers or structural isomers, you can use either name, then you're going to definitely have different properties for both types. And so pull out a piece of paper and see if you can come up with uh, the different ways to have basically here a C5H12 and see how many different ways you can put those together. Um,
Yeah, for isomers, I recommend like all of you to like just draw the skeletal formula. It's like a lot easier. Like you can basically ignore the hydrogen. The hydrogen will like be the same for no matter like how you like switch around like the linkings and stuff.
yeah, the only thing that I should mention though is that um, you can't add double bonds or triple bonds or like rings, for example, because if you do that, it changes the number of hydrogens that you have. And that actually has like to do something with like saturation and stuff like that. But so yeah, if you have the number of hydrogens fixed, then you can't like add double bonds, for example, or add triple bonds in this example at least.
Oh, also, I'm not sure if you mentioned but like for there's also the part where like rotating, they're like different. They're like the same thing.
Yeah, you want to make sure you guys, if you're drawing out isomers, that you're not accidentally making the same structure, but like rotated or something. Um, so think about if you have two structures and you're not sure if maybe they're the same structure. Think of like you were like actually there and you're looking at the structure in 3D, and if you were like to like move your head or something or move the structure in 3D, could you make it like look the exact same as the other one. If you can, then you're talking about the same structure. So different structures should not be able, in any orientation that you put them, should not look the same. All right, so type your answers in the chat. I already see you have one there. Um, and put what you think, and then we'll show the answer, and we'll show the different possible isomers. Okay. So I'll show the answer here. Um, it is three, and here are the three. So you can just have pentane, which is just 5 carbons in a row, like that. Then you can have sort of a methyl group here coming off of one of the carbons here, and so now you have, if you look at the name here, 2-methyl butane. So the but means that there's four, that the main carbon chain here, the longest carbon chain is 4 carbons. So that's this chain here. And then you have a methyl group that's coming off of it, and it has the 2 right before it, which means it's at position number 2, which sure enough is 1, 2, 3, 4. It's coming off of the second carbon here. If you were to think about it, if this was number 1, if you put 1-methyl butane, then actually that would be wrong, because you'd just be basically describing this molecule again. You'd be describing pentane, since you'd still have a 5-carbon longest chain that's continuous. And then the third possible one is this sort of like cross-looking thing. And the name here is dimethylpropane. And so let's again look at the name. It says prop, which is 3 carbons. Because if you think about it, you can only ever make a chain of 3 carbons that's continuous. And so you could do it in any possible way.
Yeah,
And
for this one, you could count the longest chain in both directions, in the upper direction, and because obviously the longest chain is the same.
mhm.
So
So no
yeah,
matter how you look at this, there's only 3 continuous carbons I can count. And then the name here is 2,2 dimethyl, and so that's to say that you have 2 methyl groups that are coming off of the second carbon. So again, in any orientation that you approach this from, it will be the second carbon here, the one that's in the middle, that has 2 methyl groups coming off of it. So that's again the name. And so there's only 3 possible isomers. Um, if you were, for example, to put this methyl group in the third position here, you would be describing the exact same molecule. It's just think about like rotating it 180 degrees, and it'll look the exact same. So that can sometimes trip you up. So make sure again you're not talking about the same structure but in different like orientations. Okay, and so talking about orientations and all these things, let's talk about what's called stereochemistry. And so stereochemistry is sort of this is sort of a specific study of once you've looked at once you have 2 molecules that have the same molecular formula, and they also have the same like constitution, the same order of atoms bonded to each other, you can still have different types of molecules. And so this is what's called looking at the configuration of a molecule. And so it has to do with like sort of the 3D orientation of bonds. Um, and this occurs whenever you have what's called a stereocenter, which is a molecule, usually a carbon, that has 4 things bonded to it, and those 4 things are different from each other. So it has 4 different possible things, and these are also called substituents. You have 4 substituents connected here. And so in this case, you have a bromine, a chlorine, a methyl, and a hydrogen. And so these are all different. Um, And also keep in mind, if instead of a hydrogen we had here like an ethyl group, which is a carbon chain of 2 carbons, this would also be different. So even though you have 2 carbons, one is part of a methyl and one is part of an ethyl, so it's still considered 2 different substituents. And if you remember back to like your orbital geometry, you would know that this would have a tetrahedral structure. And a tetrahedral structure sort of looks like you have like these 2 things like sort of bent from each other, and then you have 2 things at the top also bent but in a different orientation. And this picture here is supposed to sort of like represent that. If you can sort of see the I think the red here is supposed to be the bromine, the chlorine is the green. Um, and so you see how like this is the tetrahedral structure, and what I have here is 2 different molecules that have the same overall formula as you can see, but they're actually different. And the only thing that changes here is whether I have this dashed line here or this wedged line on the bromine or the chlorine. And so these are called wedges and dashes. The wedge means that that atom that's connected to is like sort of pointing towards you, while the dashed line means that it's sort of pointing away from you, away from the screen. And so in this top molecule here, we have the chlorine that's sort of coming out to you, and that's this green atom, and you can sort of see how it's sort of coming towards you. And then your bromine is dashed, and it's pointing away from you. And so in this picture here, you sort of see how it's like towards the back of the carbon here. And then in this second one, it's the exact opposite. And this is actually two different types of molecules. Um, so it's the same, it's a molecule with the same molecular formula, same constitution of atoms, but it has a different configuration. And this can mean that your molecule has different properties as well, which we're going to explore. And so you want to be comfortable with using these dashed and wedged lines here to represent substituents that are pointing towards you and away from you. So when you have two molecules that have the same molecular formula and constitution that we've talked about, but they have different configurations, that's what we call a stereoisomer. So an isomer was just something that had the same molecular formula but had maybe a different constitution. A stereoisomer, specifically talking about stereochemistry, which is sort of the study of the configuration of your molecule. Um, and there's this vocab here that I want you to get used to, which is called superimposable. And that's sort of this idea that I was talking about before, that if you rotate a molecule, and if you have two molecules and you rotate one of them, and then it makes that molecule look the exact same as the other one, then they're called superimposable, and they're the same type of molecule. And so in this example here, um, you have here this six-membered ring. It's cyclohexane here, and then it has a chlorine that's coming off of it that has a wedge, and so that means it's pointing towards you. And then in this other one, you have a chlorine that's pointing away from you. But if you were to think about it, if you were to take this one on the left and you were to just rotate it 180 degrees, like sort of on this vertical axis, if you were to do that, the chlorine would rotate 180 degrees and start pointing away from you, and it would look the exact same as this molecule on the right. So this is actually the same type of molecule. These two are superimposable to each other. These two drawings are superimposable to each other, and so there's the same molecule. They're not going to be considered stereoisomers because they have the same configuration. But what if they did have different configurations? And here's a very similar type of drawing, but you're going to see why this is different. So we have two different types of stereoisomers. One's called an enantiomer, and another one's called a diastereomer. And so an enantiomer is, I think, not too difficult to understand. It's two molecules that are basically mirror images of each other. But once you get the mirror image of it, they're not superimposable anymore. So they're not the same molecule. And this is the example here that I used. Um, this uh, you have this drawing here that has a chlorine substituent and a methyl substituent. And if you were to mirror it, if you were to imagine like a vertical line here that's a mirror, and you were to mirror this image, it would look like this. And unlike the one that we saw previously, you cannot rotate this molecule to look the same as what it looked like before you mirrored it. And so here I have a 180-degree flip of this molecule here. And so you see now the chlorine and the methyl were um, instead of wedges, you start using dashes instead, since you rotated that 180 degrees, and also the methyl moves sort of to the other side because you're rotating it 180 degrees. And so these two here are the same molecule, the two on the right, but neither of them are the same as this one in the beginning. Okay, and the reason to do for this is to do with like symmetry and stuff. So if I was to go back to the previous image, you see how there is like an axis of symmetry within this molecule. If you were to draw a vertical line here, um, like down the chlorine bond, um, it's symmetrical on both sides. And so it's sort of its own mirror image. And so that's why you could flip it and it'd still be superimposable. But if you do the same thing to this one, there's no axis of symmetry for this molecule. So that's why its mirror image is not superimposable to it. And so what we do here is that um, an easy way to know if two molecules are enantiomers to each other is that, like, if I'm comparing this molecule all the way to the left and then this one here that's on the right, um, you can see how both the wedges are flipped from a wedge to a dash. And so that's a sign that those are enantiomers, that every wedge and dash basically flipped with each other. In comparison, a diastereomer are two molecules that are not superimposable to each other, so they're not the same molecule, and they're also not mirror images of each other. And so in this example here, I have again the same molecule from before, but instead of flipping both wedges to become dashes, I only flipped one of them. And what this means is that you can't, first of all, you can't rotate this right molecule in any way to look like the left molecule. Um, and you also can't rotate it in any way to make it look like the mirror image of this molecule. So this is what's called these two are diastereomers to each other. And so again, the key words there or the key things to look for is that in enantiomers, those are mirror images. All the wedges and the dashes have been flipped, while in diastereomers, they're not mirror images of each other, and not all the wedges and the dashes have been flipped. Okay. And another category here of stereoisomer or stereoisomerism is when you're looking at double bonds. So this is not something we're going to get into today, but single bonds can rotate, which is sort of a weird thing to think about. But if you were to think of like your pencil and something was attached to the end of that pencil, you can sort of rotate your pencil and it rotates the things that are on top of that pencil with it. A double bond cannot rotate, and that's because of like orbital interactions and stuff. But a double bond cannot rotate, and so the actual orientation here um, of the substituents matters. So in this case here, we have each carbon has a methyl group and a hydrogen attached to it. And in this case here, the two methyl groups are on sort of the same side. They're both up here, and so this is what you call a cis, um, like a cis double bond here. But then in this example here, you have the two methyl groups on opposite sides, and this is called a trans double bond here. And the overall category, this is geometric isomers. And again, these two molecules are going to be different because you cannot rotate this double bond to make it look like the other one. So this is two different molecules as well.
So if you go back to the previous slide, I just want to mention something quick about naming that I might not have mentioned earlier. So you might also be wondering like this 2-butene thing, like why couldn't you call it 3-butene? Because technically this double bond here like is positioned between the 2 and 3, and so actually like you have to like name it based on the lower. You have to go for the lower number, and that's why it's butene.
Mm. And also you can see here the cis trans is part of the name. Um, when you're working with double bonds, you also have to specify whether you're talking about a cis double bond or a trans double bond. And there's some really complicated like rules for figuring out for more complicated molecules that like we're not going to go over because it's like too much. Okay, and so here we have a sort of diagram, a flowchart of all the relationships between molecules. And so starting here at the top, if you have two compounds, first thing you want to know, do they have the same overall molecular formula? So do they have the same number of each atom? And if they don't have, then they're not even isomers. You're talking about like, I don't know, water and like carbon dioxide. Okay, you're talking about different molecules altogether. But if they do have the same molecular formula, then you're talking about isomers. And the next thing you want to look at is are those compounds or are those atoms connected to each other in the same way? And so this was that thing again when we showed like we were asking about like what are the constitutional isomers of like C5H12, and we came up with three possible ones. So that's that. That's a constitutional isomer or a structural isomer, either name. And so here's an example of that. They have the same overall molecular formula, but those atoms are bonded to each other in different ways. But if they have the same constitution as well, so they're bonded in the same way, then they're called stereoisomers, and this is what we were talking about before. Um, and here's this topic that we didn't talk about that has to do with the single bond rotations that I mentioned, and this is called conformations. And it's basically just saying, again, single bonds can rotate, and so just because two compounds don't look the exact same doesn't mean it's not the same compound, because you might just be like one single bond rotation away from looking like the exact same molecule. And so that's like a slightly different topic, but it's not covered too much on the exam, and it's not too difficult either to understand. So we didn't cover that. But so yeah, if you could just rotate one of the bonds to make it look like the same, then you're talking about a conformation. And technically those are also the same structures. But if you can't do that, then you're talking about a configurational isomer. And this is the thing we're talking about. If you have a double bond, then you're talking about a geometric isomer, configurational isomer, and that's the thing about the cis and trans. Um, But if you're not talking about a double bond, you're talking about a tetrahedral center. So again, that's a carbon with like 4 bonds to it. Then I guess the technical name here is an optical configurational isomer. And then this is the whole thing about, are they mirror images of each other? If they're mirror images, then they're enantiomers. If they're not mirror images, they're diastereomers. And you can imagine an enantiomer or a carbon or a molecule will only ever have one other enantiomer. So there's like one pair of possible mirror image. And so there's always two. While diastereomers, you can have multiple different types of diastereomers depending on how many stereocenters are inside your molecule. Okay, so that's going to be sort of it for this part. We might have another meeting talking about other stuff and talk more about reactivity of organic compounds, but we wanted to sort of just give you an idea of the basics, which is naming and stereochemistry, because you really have to sort of understand this stuff before you can really get into the more like predicting reactions and stuff like that and predicting like the products. Um, we understand this probably a lot, and we don't blame you if you feel a little bit lost. This is again sort of more of an introduction to the topic, and you can then sort of know where to look if you want more information. Like let us know if you want like I don't know textbook chapter recommendations or some crap like that, um, and we'll let you know. Um, but yeah, if you have any questions, ask us either in the voice chat or in the chat. We'll try to answer it. But if not, then you're free to go, and we'll announce in the remind next time we have another meeting. But yeah, thank you guys for joining us. Thank you, Akshay. Have a good day. All right. Kind of a
And
quiet meeting today. Oh yeah. All right. Thank you guys in the video and the YouTube recording for watching. We'll see you guys next time.